Okay, so I know this was probably a long time ago for many of you. And then you ate turkey and watched football and you forgot all about modular expression. So hopefully you've done enough stuff with the mod that you kind of remember what it is. The tricky one is the negative ones, remember. Okay, so we are looking at modular arithmetic and some applications to finish up this section. So we've got a theorem that's very useful. We'll see when we look at doing some of the encryption algorithms that these in particular come into play. Knowing these rules is very handy because it helps us do arithmetic with these very large numbers. It allows us to kind of reduce them. So if we have m that's any integer larger than 1, and we have x and y that are just some integers, and we're trying to do x mod m plus y mod m, and that sum also modded m, that's the same thing as just adding the numbers and doing mod m. So usually the context is you're trying to do x plus y mod m, okay? And if x and y are large numbers, it might be more convenient to first do x mod m and then do y mod m to get those reduced to numbers that are less than m, right? Because the remainder will always be a number between 0 and m minus 1. Okay, so you have these much smaller numbers to work with, and you can add them together. Well, still, just because you have two numbers less than m minus 1 doesn't mean their sum is less than m minus 1. So you'd still have to, after you added them together, do a mod m again. Okay. And the same thing applies if you're going to multiply. So if I'm going to take a product of two numbers and do it mod m, okay, so we can stay in that ring like we talked about last time, okay, you can, again, apply the modulus to the individual operands first, then take the product of their modular results, and then again, if you get a number that's larger than m, you just do the mod m on that one. So let's look at some examples of where this might come in handy. So let's say you wanted to do 42 to the 7th mod 5. Well, if you go and put 42 to the 7th in your calculator, it's a huge number, right? And then you put it in exponential form, and it's really hard to work with. So doing 42 to the 7th is a little bit tricky. But if we realize that 42, if I write this, imagine what this means. This means 42 times 42 times 42, 7 times mod 5. So if I apply this rule right here, well, I could individually mod all of these things, and this is the same thing as 42 mod 5 times 42 mod 5, okay, 42 mod 5, 7 times, okay. And then, of course, at the end of that, we're going to have to do mod 5. But this, we can just actually do in our heads, because what is 42 mod 5? 2. And so this is just the same thing as 2 to the 7th mod 5. And now, 2 to the 7th mod 5 is way easier than 42 to the 7th mod 5. Okay. You might even know what 2 to the 7th is. Anyone? Did somebody say 46? Okay, no, it's not 46. 46 is not even a power of 2. Are you thinking 64? Oh, 256. Okay. 256 is close. That's 2 to the 8th, right? It's 128. So this is 128 mod 5. And you probably know what 128 mod 5 is. It's pretty easy, right? That is 3. Yeah, it's 3. Right? So we could do all of that, and we never even needed a calculator. Later on, when we do some of these things, we are going to have to break out a calculator. Okay, but it's fun. We get to choose which calculator we want to use and everything. It's exciting. Okay, so Very handy property, because if you try to do this all in your calculator and raise 42 to the 7th power and then try to figure out what the quotient of that one, it would just be a big pain. Okay, but if you do everything, all the mods first, relatively easy, and you can probably figure it out in the time it would take you to unzip your bag, pull out your calculator, take off the cover, turn on the on, but you know, like, you could be done by the time you did all of that. Okay, so let's look at this next one. This is going to be a similar kind of situation. So we're going to do, okay, this. If I wanted to figure out what all of this was, mod 8, I would do the 57 mod 8 first, and then raise that result to the 12th power, just like I did back here. I did the 42 mod 8 and raised that to the 7th power. And of course I have to do mod 8 after this. And then minus, and this will be 17 mod 8 times 78 mod 8. Sorry, I'm running into my old one. Okay. And then you'll want to take that whole product and then do mod 8 on that as well. Just mod 8 everything. Okay. And so, what is 57 mod 8? That's 1. Yeah, so this is just 1 to the 12th mod 8. And I think we can all do that in our brain. And that's much easier than doing 57 to the 12th power on your calculator. Okay. And then what is 17 mod 8? That's also 1. And 78 mod 8? 6. Okay. Oh, why did I put mod 12? Oh, because of that 12. Hopefully you did not write mod 12. Or you were asking yourself, how did it become mod 12? I'm sorry. Okay, so 1 to the 12th is, of course, 1. And 1 mod 8 is 1. So this part is just 1. And then 6 times 1, of course, is 6. And 6 mod 8 is 6. Okay, and so this is negative 5. Once again, we did not even need to break out the calculator for any of this. Okay, so these properties come in handy, especially when you're dealing with large values like this. You would not want to have to go into your calculator and do 57 raised to the 12th power and try to divide that by 8 and see what the remainder was. That would be miserable. So much easier to just do 1 to the 12th. Okay, so super handy. Yes?
What if you write mod 8 again? Isn't each one of 57, 17?
Yes. So imagine, like, for instance, that I was trying to do 78 times 78 squared mod 8. Okay. So when I did this one, when I did 78 mod 8 times 78 mod 8, well, this one is 6, and this one is 6, and when I multiply that, I get 36. Now we know that I'm doing something mod 8, and my answer has to be between 0 and 7. Okay, so these individual numbers were between 0 and 7, but that doesn't mean the final answer will be between 0 and 7, right? So I have to continue to put mod 8 at the end of it to make sure that my final answer is between 0 and 7, that I'm actually staying in that ring, that 0 to 7 value. Yeah, so if I do that, then I'm going to get 4, right? So it just makes sure that I have to do that final mod to the answer so that I can make sure that I'm looking at a remainder and my answer will definitely be less than 8. Yeah. Good question. Okay. And so, where might this come up in writing some kind of computer program? So I came up with the 3 most common examples I could think of. Okay, so in fact, if you are taking data structures right now or have taken it recently or will take it in the future, then you haven't seen it yet. But if you've taken data structures already or if you're taking it now, you've probably seen something with a circular array, okay, like to implement a queue or something like that. Okay, so a circular array is just an array that folds back around on itself. So normally we think of an array as, being just a linear list, kind of like this thing over here. But a circular array is going to go around, okay, like this. Okay. And so maybe this has index 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then you go back to index 0, and when you fill it up, it's a finite array, and it's got 10 elements in it, numbered 0 through 9, and after you get to 9, you go back to 0, and you just go around and around and fill it up. So often, if you have taken data structures, you'll use something like this to implement stacks or queues or things, because it's a very efficient. You don't have to move things around in your array and shuffle them back a lot. You can just kind of go around in a circle and put things into the array. So, how many people have actually used circular arrays to implement something like a queue? Is anybody taking data structures right now?
Yeah.
Okay. Oh.
Yeah.
I mean, I learned just now.
Okay.
It seems very simple.
Okay, yeah, so it seems, okay, so, all right, actually so do you just use like the queue data structure that they give you in some package and they don't make you figure out how to implement the queue? You just kind
if you have like a hash table, and then like you just draw a linear hash table, and then like if it goes to the next one, we just draw the next one. We don't write it in a circle.
yeah,
We
okay.
still just write it linearly and then just pop it over the next.
Okay, so, yeah, but you're using some kind of a hash table. So you're not actually seeing how it's implemented, you're just using some, okay. So if you ever look at actually how these things are implemented, they're often implemented with some kind of a circular array. Okay, and so, like, let's say I was wanting to, like, add an element to the array, okay. This is also comes up with, like, this one over here is buffer is the same idea. So a buffer, like, it's like an array, but it wraps around on itself. And so, like, lots of embedded systems programming or even just buffered I/O where you're putting stuff into a buffer because, you have devices with mismatched speeds. And so one thing is reading, one thing is writing. Same kind of thing. It looks like a circular array. So you're going to fill it up. So this buffer, like there's a read position. Like if I'm typing, okay, as I type, my keyboard input, if it's going to go into a buffer, okay, this write position will advance and put in all the characters into my buffer. And then, if you've ever written a program in C, you have all this weird, like, I/O stuff where you have to flush your buffer and stuff like that. Have you ever run into this? You haven't done as much C programming? Yeah, mostly C++. Yeah, if you haven't done a lot of C programming, a lot of this stuff gets taken care of for you, but if you do it in C, you have to kind of take care of it yourself. And the I/O is very kind of weird. But then when you have, like, a cin kind of statement or a reading, well, it'll just go to wherever your read pointer is in your buffer, and it'll read as much as you've asked it to read. If you ask it to read a byte or whatever, or if you ask it to read until you see like an end line character, it'll just advance that reading pointer. Okay, but the buffer is finite, and so you pick a certain size for it. And every time you write, it'll keep writing in the buffer, and it'll turn, and it just keeps writing around, and then the reading will go behind it. And as long as the write pointer stays above the read pointer, it can overwrite over old values, and the buffer works perfectly. If the write position ever catches up to the read position, the buffer will fail, and you'll get some kind of an exception. Okay, so these are two different kinds of circular kinds of applications where you all see, and if you're going to implement this stuff, the modulus operator comes in handy. So let's say over here where I'm looking at, well, let's do this one. It's the same thing over here, but this one already has a read and a write position. So if I'm wanting to, advance my pointer and for here, my write index, it looks like a pointer, but it's an index. Okay, so to advance the write index, okay. Normally you just think I'm going to do, okay, write equals write plus plus. Okay. Or write plus 1, however you like to increment. Okay. And that works well. You start out at 0, you advance it to 1, you advance it to 2, and you just do plus plus plus, but then you get around here to 15. And if I go write plus plus, it's going to go to 16. But there aren't there is no buffer with an index of 16 in it. Okay. So the way that I would take care of that is once I get to 15, I'm going to do right plus plus and do my mod, whatever my buffer size is, in this case 16, we'll just do it for this example. So once I get to 15, okay, to get to the next right position, I'll go advance this to 16, mod 16, that'll become 0, and now my next right position is at buffer 0. Okay. Same thing to advance the read pointer, or the read index. You'll do the same thing, so you do read is read plus plus, and make sure that you do it mod 16. And this isn't Python, so I can put semicolons at the end. Okay. Okay. So same thing in a circular kind of array. If I were wanting to add things to this array, to get to the next index, I would just do the index plus 1, but then when I get around to but I would have to do mod 10 in this one. So anything that wraps around and is circular in nature, when you encounter that in the future and you see this kind of wraparound or circular nature, you're going to go, oh, I'm going to have to use a mod operator on that to make it wrap around. Okay. Another place, this is another wraparound kind of thing, but maybe in slightly different context. So something called a rotational substitution cipher. And I got this little picture off of Amazon. Apparently you can buy this little Caesar cipher thing, and it's like you and your friend can have your secret code, and you turn this little dial around and it shows you how to make this secret, so you can pass secret messages back and forth. Okay, so the idea with a rotational substitution cipher, so a substitution cipher is where you take the letters in your alphabet and then you substitute them with some other symbol. So that could be some crazy symbol like you see on the back of your cereal box when you were a little kid, or some little, I don't know, book that had like triangle is for A and the star was for B, and so it doesn't, but it's often more likely that we're going to substitute one letter for another letter. Okay, and this is called a rotational substitution cipher because you can see like this has A through Z on it and this has A through Z on it, and you just take this inner ring and you rotate it a little bit. Okay, and then based on how far you've turned that, whatever, here A lines up with B, so I would substitute A with B and B with C and C with D. That's how I've rotated it. Actually, I've rotated it 25 positions. I think you can even see that in there. Does it say 25?
It does.
Yeah, it's kind of, I can't see it very well, but you've rotated it clockwise 25 positions. This one is an example where I've taken this and I've rotated it 19 positions. Okay, and so whenever I see an A, I'll substitute that with a T. Whenever I say B, I'll substitute that with a U, and so on and so forth. Okay, and so if we have let's say this is our original message. I'll just call it message. Okay. Let's say it was something like math. Oh, they had it in capital letters. Let's do capital math. Because that's shorter. That's a short word. Shorter than computer or something. Okay. So, and you want to figure out what this, so let's say, in this message, 0 is the capital M, and message 1 is a capital A, and so on and so forth. And now you want to figure out what the secret message is. That's called the cipher message. So if I want to figure out what the cipher message is, okay, well, you would take the original message, okay, so if I'm going to find cipher 0, I'm going to go to this, and then I'm going to add however far. So let's say, then this one where I rotated it 19. So this is normally 0, 1, 2, 3, 4, 5, 6, 7. Let me just write them all. Okay, so A is 0, all the way around to 25 is Z. So this has a key of 19 because this inner ring has been turned 19 positions. Okay, and so if I take and add whatever my key is, in this case, 19, but it could be anything. Okay. So let's think about what will happen. So if in my example where I have message 0, okay, that's an M. So here's my M. That's at index 12. Okay, so this is, I'm going to have to convert this to a number. Okay. Okay, so get the number for message 0. So that's 12. And now if I add 19 to it, 12 plus 19 is 31. But there isn't a character 31. Okay. But this whole thing is circular, so if I take this whole thing and I do it mod 26, because there are 26 letters in the alphabet, that will make sure that I go back, okay, and I'm only going to get a letter from the alphabet. So 31 mod 26 is 5, okay, and so cipher 0, okay, would be this thing, whatever 5 is, and I better turn this into a 20, 31, no, it's 5. Because 26 goes into 31 once with 5 left over. Okay. Okay, and so if we go to the 5th character here, okay, that would be an F. Okay, so it would get stored as an F. And if you notice over here, this M maps to an F. That's correct. Okay, so you can see on the key that M does map to F. Okay, from the little ring, but if you were to write this as a computer program, you'd take your message, turn it into a number, add the key, mod 26, and then I've got to turn this thing back into a character. Okay, and so I would get the number 5, and then turn that into a character. Character 5 is F, and that would, so this cipher 0 would become F. Now imagine we did it with character A. So we would do A, that's 0. Okay, add the key, which is 19. 19 mod 26 is still just 19. That one doesn't even really need wraparound. And character 19 is a T. And see that A maps to T. So anytime you see this circular wraparound, that modular arithmetic is going to be involved there. And then if you wanted to go backwards, let's say you got this secret message that was, F whatever. So if I wanted to go, from the cipher message to the original message, I would just do the reverse of this. So I would take my cipher at index I, and I got to turn that into a number. I'm just going to pretend that's a method. Okay, well, I'll just do 2num of this. And then I would just subtract the key to make it go backwards. And then do this mod 26. And take that whole thing and turn it into a character. And that would give me back my original message in the ith character. Okay. So if I want to, so I would add the key, that's like turning it clockwise, okay, to get the hidden message, and then this simulates turning it counterclockwise, subtracting off the key to undo what we did if I want to get back the original message. So imagine, we had this F here, okay, and I want to see, well, what did F come from? So my cipher one would be F. I would go look up that number, F. Well, F is 5. I would subtract the key. I subtract 19, so I get negative 14. And what do I get when I do negative 14 mod 26? So let's try it up here for a second. So negative 14 mod 26. There has to be something times 26 plus a positive number. So what would I multiply my 26 by? -1. And so then what would I have to add as my remainder? That would be 12. Okay. So that would be 12. And when if I went to character 12, that would be M. And sure enough, I'd get my M back. Okay. So, any of these kind of little, like again, that's because it's circular in nature. This rotational substitution cipher is circular in nature. So anytime you see something that wraps around or is circular, that is the key to you. I need to use some kind of modular arithmetic here. Okay. Okay. The next one that I thought of that you might come across is extracting digits from a number. I'm going to have to carry over onto this page. So let's do extracting digits. So say, for example, a problem like this. You have a number, an integer n. And let's just say that it's greater than 0 for the sake of it. Okay. And you want to find the number of even digits. So let's say, for example, I have the number 1. Well, let's do 1, 2, 4, 7, 8. And I want to, figure out how many even digits does that have. Okay. So how would you do something like this? Ideas.
You could use the mod operator to iterate through each digit of it and use if statements to see if number's even, if number mod 2 is 0 and it's even, so you can have 2 other variables holding the number of evens and the number of odds.
Okay, good. So let's just go ahead and write some code. It might not be, I don't know if this will be C or Java, or it'll be a mixture of all of those things. But we'll have called, num even. Okay, and we'll start that off at 0. Okay. And then I don't want to let's say I don't want to destroy this number. Okay, I'll just call this current. And I'm going to start that off at n. So imagine this is my n value right now. And then I have my num even. I'm going to start that off at 0. Okay. And I could say, while my current value is greater than 0, I think that should work. Okay. So, how am I going to, so which digit am I going to look at first to check if it's even or not? And you're saying iterate through the digits. What am I going to, if I'm thinking about doing mod and div kinds of operations, what is going to be the easiest digit for me to pick off of that number? The first digit or the last digit? The last digit, right? Because if I want to get that digit, how can I find that digit? Mod 10. Okay, so I'm just going to call this last digit equals current mod 10. Okay. The last digit right now. Oh, sorry. So my last digit right now, if I do this mod 10, divide this by 10, the remainder is going to be whatever's in the ones place. That's going to give me an 8. And then I can just say, if last digit mod 2 is 0. Okay. Is there a then there? I can't remember. Okay, and then the number of even will go up by 1. Okay, so for our example, well, that's an 8. That is even, so this would go up. And now I found one even number. Okay, and now what should I do? I've seen the 8, I want to throw that away, and I only want to consider the rest of it. So how am I going to now just hold on to the 1, 2, 4, 7 and throw the rest of it away? not mod, but
Divide.
yeah, divide. So if I take my current and do current and then divide it by 10, that's going to do integer, or the div operation, right? And so this will become 1, 2, 4, 7. I think we're going to have to change this condition. I think this needs to be, well, the current is greater than 10. Greater than or equal to 10. No, I was good. It is good. Sorry. It'll be good. I'm trying to do the whole thing in my brain. Yes, I think it's good. Okay. So let's see if we come back around here. So current is still bigger than 0. So we're going to come here. The last digit would be current mod 10. So that's going to become 7. Okay, so if we take 7 and divide it by 2, we're not going to get a remainder of 0. So that one's not even. We won't count it. Our current will become 124. Is that bigger than 0? Yep, it is. So we come in here. The last digit of that one is 4. That one's even, so we'll increment it. Current becomes 1, 2. That's still bigger than 0. The last digit of that one is 2. That one's even, so that one will count. Come back, current becomes 1. That's still bigger than 0. The last digit of that is 1. That one's not even, so we won't count it. And then when we get to current equals current divided div 10, what is, oops, that should be current. Current is current div 10. What's 1 div 10? 0. Okay, so yes, this was good. So current isn't any longer. So we'll come out of it, and we've counted 3 even digits, 8, 4, and 2. Okay. So a great way to pick the digits off of a number for whatever application you might need, you're going to have to use both mod and div. Okay, so that's a nice little, probably bad syntax. There is a then there, right? So, I don't know. I've done Python most recently, and there's no then. And so
There's no then.
there's no
C++
then.
either.
Okay, there's no then. It's just a bracket. Okay, except that we only have one, so we don't need a bracket on this one. All right. It's been a while since I've programmed in C++. Okay. That you might be able to type in if you declared your variables and types. Okay. All right, so very good. So, hopefully that will stick in your brain if you ever see, like, oh, I need to pick off digits, or I have something circular in nature, or something that wraps around. You know that mod, it's going to involve mod in some way. Okay, so that does it for section 8.2. Next we'll look at section 8.3 with prime factorizations. Okay, so one of the important things from this section is something called the fundamental theorem of arithmetic. Okay. So to get to that fundamental theorem, which is actually down here, it's all about prime factors. So prime numbers are the building blocks of all integers. Okay, and yet sometime in your life you've probably had to do prime factorizations, probably when you were younger. And you probably already know, and this isn't news to you, that every single positive integer greater than 1 can be expressed as a product of primes, and that's called its prime factorization. Okay. So the fact that every integer has a unique prime factorization is a central idea in number theory, and that's called the fundamental theorem of arithmetic. So if I take the number 180 or the number 280, there's only one prime factorization for that number. They're not like 3 different ways to write the prime factorization. There's only one. And you know that because you've done it many times, but that is actually an exciting and amazing important fact in number theory. Okay. And then the multiplicity of a prime factor is the number of times that it appears as a prime factor. So let's say maybe you used factor trees or something like that to do this in your past. So we'll see if you do it like I do it. So is this how you do it? You like do a little factor tree to find them? All right, so if you were gonna do 180, what were your first two factors you think of?
20.
You think of 20? Okay, I heard
90 and 2.
you thought of 90 and 2. Like, I just think of 10 and 18. Like, there's a 0 there. I don't know. So I don't know. Pick your favorite ones. You can do it however you want it. Okay, we'll go ahead and do 2 and 90. Then when you do 90, do you think of 10 and 9?
45 and 2.
45 and 2.
I always do the 2s.
Oh, you always do the 2s. All right.
That way everything's on one side.
Yeah, that's true. That is nice to have them all there. No more 2s. So now you go to the 3.
2 and 24. No, now I go to
Now you do what?
Now I go to 9 times 5.
But why not 3? You did 2s.
5 on the end.
Yeah, that's fine.
But there was a 0 on the end.
I'm
But
with
it's
him.
also even, so you divide it by 2.
Oh, yeah.
Okay, so you're not, your goal is not trying to make it go like 2s and 3s and, okay, all right, I'm gonna just go with it. So 5 times 9, and now, no, okay, and then you go down to 3 and 3. I just like, we were doing the 2s, I thought we would do the 3s next. Okay, no, all right, no, that's not how we do it. Okay. So I would have done 180 is 18 and 10, and this would have been 2 and 5, and this would have been 2 and 9. But then I would have had my 3 and 3 here.
It's a little more balanced like that.
Yeah, I don't know. So either way, you get the same thing, but okay. So however your brain works it out, just if you like the even numbers and then, oh, this is obviously a multiple of 5. Like to me, I just look at this and go, oh, this is obviously a multiple of 10. That's just what I think. I don't know. So in the end, like we get 2 times 2 times 3 times 3 times 5, but you probably don't write it like that, right? You probably write it as 2 squared times 3 squared times 5. Okay, and so the idea of the multiplicity, that's how many times a prime number shows up. So if I like write it all out the way I did when I was a little kid, I see that 2 appeared twice, or here I see it as an exponent. So really here the exponent, so the multiplicity of 2, of the factor 2, is 2. Here the multiplicity is 2. And then what about the 5? What's its multiplicity? Yeah. So it's just 1. Okay. So if you just look at the exponents, you'll see what the multiplicity of that prime factor is. And if there isn't an exponent there, remember that's an implied 1. So it has multiplicity 1. Okay. Maybe some of you, rather than writing trees like this, maybe you did it like 28 times 10, and then underneath that write this as 4 times 7 and 2 times 5. Okay, well that's prime, that's prime, that's prime, but this one isn't, so you write this 2 times 2 times 7 times 2 times 5, just replacing every composite number underneath. So some people do it that way. Okay, and then in the end you would get 2 cubed times 5 times 7. So those are the kind of the 2 ways that people are taught. I don't know which one you were taught. Okay, so what's the multiplicity of 2? And then the multiplicity of 5. 1. And 7 has multiplicity 1 as well. Okay. So hopefully that's review, and you can pick your favorite way, your factor tree or your replacement, one line after another. They all do the same thing.
So what's the answer then? Just like the multiplicity number, or like
So the prime factorization would be 2 cubed times 5 times 7. But then if I were to ask you a question like, what is the multiplicity of the factor 2 and the prime factorization of 280? And you would want to tell me, oh, it has multiplicity 3.
okay.
Yeah. So the prime factorization is here, and I'm just trying to point out what the multiplicity of the factors are. Okay. And these multiplicity of factors come into play when we need to find the greatest common divisor and the least common multiple. Okay, so again, I'm sure these are things that you have done in your past, but maybe it was a while ago. So the greatest common divisor is, of course, the greatest or largest integer that will evenly divide, if we're just talking about x and y, both x and y. Okay, so it is the largest positive integer that would be a factor of both of those. Okay, and sometimes people get that confused with least common multiple. So the greatest common divisor is going to have to be a number that is less than or equal to x and less than or equal to y. It has to be less because it has to divide them. It can't be bigger than x and it can't be bigger than y. Okay. Then the least common multiple of two integers is the smallest positive integer that is an integer multiple. And if you think about multiples, okay, multiples of x are x, 2x, 3x, 4x. Multiples of y are y, 2y, 3y, 4y. So the smallest thing that the least common multiple could possibly be, it has to be bigger than x or bigger than or equal to, and it has to be greater than or equal to y. Okay, so that's one kind of way to can help you remember if you get confused between them. The greatest common divisor has to be less than the smallest one of x and y. And the least common multiple has to be greater than or equal to the largest of x and y. So that can help you make sure that you don't get them mixed up. Okay. And finding the greatest common divisor or the least common multiple is really easy if you know the prime factorization. So if you just go through the prime factorizations for the greatest common divisor, you go through all the prime factors, and for each prime factor, you pick the smallest exponent that ever appears on any factor, and then you use that to find the greatest common divisor. And then, so you pick the smallest exponent for greatest common divisor. For least common multiple, you use the largest exponent. So let's do an example. We have our 180. Let me write these out. So 180 is 2 squared times 3 squared times 5, we figured out. And 280 is 2 cubed times 5 times 7. So if I want to find the greatest common divisor of these two, I'm going to... Oh, thank you. So if I want to find the greatest common divisor, I'm going to go through and I'm going to list every prime factor that appears in these two numbers. So 2 appears, 3 appears, 5 appears, and 7. Those are all of the factors that appear in the prime factorizations of these two numbers. And now I'm going to go through and I'm going to pick the smallest exponent. Okay, but when I do that, I should first of all rewrite this. So 7 didn't appear in this one, but I could put it in there by putting a 7 to the 0 here. Okay, and now it has 2, 3, 5, and 7. And 3 didn't appear in this one, but I could put it in there by putting a 3 to the 0 in here. Okay. And if you don't put every single one of these factors in both numbers, then you might accidentally pick the wrong exponent. So it's a good idea to put, if you're not disciplined about thinking, oh, there isn't a 3 there, that's really an implied 0. So just write them in there. I think it makes it easier. So if I want to find the greatest common divisor, now I go through every single one of these factors and I pick the smallest exponent I ever saw on that. So here the exponent of 2 and here an exponent of 3. The smaller of those is 2, so I'm going to put a 2 squared. For the 3, there was an exponent of 2 from the 180 and an exponent of 0 from the 280. The smaller of those two is 0, so this one's going to be a 0. Okay, both of these had an exponent of 1, so I'll just keep it as a 1. And then the smallest exponent on the 7 was a 0, so between 0 and 1, so that will be a 0. So my greatest common divisor is going to be 2 squared times 3 to the 0 times 5 to the first times 7 to the 0, or 4 times 5, which is 20. Okay, so the greatest common divisor is 20, so if you're probably more like most people where they just intuitively kind of sit there and think about it for a while and go, yeah, it's 20. But there is a process to figure it out. Okay, then the least common multiple. Okay, essentially the same process, but instead of choosing the smallest exponent, we choose the largest exponent. So we're still going to use 2, 3, 5, and 7, but this time we're going to pick the biggest exponent instead. So your exponent of 2 and 3, the biggest one is 3. We add an exponent of 2 and 0, the biggest one is 2. Okay, both of the 5s had a 1, so the largest is 1. Okay, and the biggest of a 0 and 1 is 1. Okay. And so, let's see, we've got 8 times 5, that's 40. And we've got 9 times 7, that's 63. So that's going to be 0, 12, 20, 25, 20 as the least common multiple, if I did that correctly. If you need to break out the calculator and check me, then hopefully you can. Okay. Yeah, I checked it. It's good. Okay. So the process is very similar. It's just remember that in my answer in the end, the greatest common divisor is going to have to be less than 180 and less than 280. It is. That's a good sign that I didn't use the wrong process, right? And I know that my least common multiple is going to have to be larger than 1 or equal to 180 and larger than or equal to 280. When I get this big number, that's a pretty good sign that I did it right. So if I accidentally got the 25, 20 here and the 20 over here, I would say, wait a minute, I must have mixed up where I should pick the small exponents and where I should pick the big exponents, because this one better be bigger than those numbers and this one better be smaller than those. Okay, so now that we have that process, let's go through. Okay. Can you just, in your brain, do the prime factorization of 140? 2 squared times 5 times 7. Yeah, because it's 14 and 10. Did you, or 2 and 70?
I did 2 and 70.
Okay.
35 and 2.
Okay, so 2 and 70. Okay, and then 175 is maybe a little bit trickier. 5 goes into 175. Well, how many quarters make up $1.75? 7. 7 quarters. So this is 7 times 25, which is 5 squared times 7. Okay, so we've got our prime factorizations there. Okay. And this time we'll do it without writing our 2 to the 0 for those of you that like shortcuts. Okay. And we'll discipline ourselves to make sure that we don't ignore it. Okay. So, when I go through the greatest common divisor, I need to pick the smallest exponent, so I'm going to pick this factor, 2. So I go, oh, there's a 2 here, but there isn't one down here. So in my brain, I make a mental note that that would be like a 2 to the 0. There's no 2 down there. Okay. So is the factor 2 going to show up in my greatest common divisor? No. Okay, because it's not common, right? Okay, so there's not going to be any 2's in there. They both have a 5. So what exponent am I going to put on the 5? A 1. So there's going to be a 5 to the first. And they also both have a 7. And so what exponent should I put on the 7? 7 to the 1. So this should be 35. Okay. And then with the least common multiple, we're picking the largest exponent. Okay. There's a 2 here. This one doesn't have a 2, but in my brain that's like a 2 to the 0. So I'm gonna have a 2. And what exponent should I put on my 2? 2. Okay, they both have a 5. What exponent do I put on my 5? 2. And then they both have a 7, so I make 7 to the for the first. All right, and we've got 4 times 25. 4 quarters is $1. That's 100. 700. All right, so that's finding greatest common divisors and least common multiples. All depends on whether or not things are factored. Okay, so, but finding factors is actually a tricky thing to do. And now you can easily write an algorithm for it. So the most obvious algorithm to write is just to go, okay, I'm gonna input some number n, and I'm trying to find a factor for it. Okay, so this is just going to output prime if n's prime. If it's composite, then it's just going to give the first factor it can find times whatever. Okay, so just going to give two integers that multiply to that number. And you can imagine if I just called this over and over again until I had all primes, I could just iterate this several times to find all the prime factors. Okay, so the way that this works is you just start, okay, well, 2 is the smallest prime number. Okay, so I don't want to think about 1 as a factor. 2 is the smallest one, so I just start at 2, and I would check, does 2 divide the number? If so, yay, return 2 and whatever n divided by 2 is. If it doesn't evenly divide it, I check 3. I mean, this is probably how you kind of go through it in your mind. Oh, 3 doesn't divide it, 4, you just kind of check them linearly. Okay, and you could go all the way up to n minus 1. Okay, but if you think about it, going all the way, if I want to try to find, factors of 107, okay, would you have to keep checking all the way up to 106, or would you know earlier than that you could stop checking? Yeah, you would know earlier, like at what point would you know that you could stop checking? So halfway is an idea. Okay, so yes, you could definitely at least stop halfway, but you can even do better than that. Yep.
Well, I'm not sure, but like whenever you go past the point of having new factors.
Yeah, so when you go past the point of having new factors, and when will that happen? That's the question. So let's think about the number 100. Okay, that's an easy thing. So, 2 divides it, 5 divides it. At what point do you know you're not going to have any new factors? Once you get to what number?
When you divide it on 2.
Well, you have 250, but there's another factor bigger than 2 that divides it. So how would you know? But so 5 divides it. But what after you divide by?
Returns to, like, you divide 550, and it should be, if you're in the set of integers, right?
Yeah, so let's say I wanted to find all of the prime factors, though. So I've already returned 2 and 10, and so I know 2 divides it. Sorry, 2 and 50. I know 2 and 50 divide it. Now let's say I wanted to find, so I have that 2 as a prime factor, but that's not its prime factorization. So let's say I wanted to know if there were any other prime factors. And so then I would check 3, and then I would check 4. 4 isn't prime. 4 divides it, but 4 isn't prime. Like, at what point do I know that, like, I'm just going to start repeating things and I don't need to go any bigger than that number because I've already found 10. Yeah. 10 is when you could stop because that's the square root. And that would be like something times something equals that number. And then once you go past that point, it would have to be multiplied by something smaller than that to get 100. And so you've already considered those when you went up to the square root. Okay, so sort of the most efficient brute force thing you can do is go up to, well, it ends up being the floor of the square root because that might not be perfect. You might not, if it's 101, then you still only need to go up to 10. Okay, so rather, it's quite, you don't have to check as many. So if you're going here, you're thinking about the number 100 and you were trying to, or the number 101, you would have to check everything from 2 to 100. Here, if you're trying to see if 101 is prime, you'd only have to check up from 2 to 10, and then you say, okay, well, I haven't found them yet. There's nothing that comes after that that's gonna divide it. Okay, so this seems like quite a bit better, and it is. But if you're talking about digits that are, have something that has 78 digits or 100 digits long, and you're just doing the square root of it, it's still a huge number with so many digits that if you're trying to check one after another after another after another, it's going to take you like 2 centuries to check all of those numbers, and it's just not feasible for you to go through all of them. And so it turns out that, with these brute force algorithms are really the only ones that we know that that number theorists have ever figured out for trying to figure out if something is prime or trying to factor something. So factoring is hard. I mean, you can write an algorithm to do it, but it takes so long that it's impractical. Okay, so if you're having to check every number and up to numbers that have hundreds of digits, one at a time, it's going to take so long that it'll say, okay, well, I'll get back to you in 275 years. Well, that doesn't do me any good if I'm trying to do something with it now. So there is no known algorithm that can solve the factoring problem of finding two factors efficiently for any random, like, arbitrary input. And that fact, okay, is what all of our cryptography systems are built on. Like, they all rely on this fact. So they pick these prime numbers or numbers that have these huge prime factors, and it's so hard to factor the numbers and so impractical for us to be able to do that, that we can rely on the fact that that's impractical for our security systems and nobody being able to break them because nobody can factor these numbers. So we will look at that. We might not get to it today. We'll get to it next time. But that's why it's important, because if anybody were to ever find an efficient way to factor like every single one of our security, we'd have to throw them out the window, and all of our networks and stuff would be insecure because everybody would be able to break at them. Okay. All right, the final thing in this section is that there actually is an efficient algorithm for testing if something is prime or not, and it is based on random numbers, and so it can with a small probability tell you the wrong answer, but if you run it a certain number of times, the probability that it's incorrect is so small that you can trust it pretty well. Okay, so we're not going to get into that algorithm, but it's based on something called the prime number theorem. So the prime number theorem says, all right, this pi of x is the notation for the number of prime numbers that there are from 2 up through the number x. So like, pi of 5. How many prime numbers are there in the range from 2 to 5? Well, there's 2, 3, and 5. There's 3 of them. That's a pretty large percentage in the first 4 numbers from 2 to x. Okay, but what happens is if we go and x gets larger and larger and larger, okay, not just the first 4 numbers, but many, the number of prime numbers, okay, divided by x over the natural log of x is going to be 1. So that's what the prime number theorem tells us. Okay, so that just seems like, okay, who cares about that? But if you think about this, okay, when x is large, I'll say very large, okay, what it's saying is that this ratio approaches 1. Okay, so when x is very large, the numerator and the denominator are basically the same. Okay, they're pretty close to each other. So if I take the numerator, x of pi of x, okay, that's roughly the same as x over the natural log of x. Okay, that ratio has to be 1, and so that means the numerator and the denominator, they're roughly the same, as long as we have a large x. Okay, and so if I solve this for, so let's say I'm going to divide both sides by x now. So I'm not really going to, so let's say I'm going to multiply this by 1 over x and multiply this by 1 over x. So that's going to give me that pi of x over x is roughly 1 over the natural log of x, because those cancel out. So if you look at this part of it right here, this is saying the number of prime numbers divided by the total number of numbers from 2 to x. So if that is like the probability of finding a prime number in the first x numbers. So this part of it right here is the probability of choosing a prime from the first x positive integers. And so that probability is roughly 1 over the natural log of x. So, and that's what this theorem is kind of working with. It works with these probabilities and says, well, it's very likely that I've chosen 1 or that I haven't chosen 1. Okay, so that's how you can interpret that, okay, is that if I randomly select a number in the range from 2 to x, the probability that I chose a prime is about 1 over the natural log of x. Okay. So when you do your homework, they'll ask you some questions about, oh, what's the probability that you chose a prime number in the first 100? Well, that would be about, 1 over whatever the natural log of 100 is. Okay. So we've got enough time to at least start this. Okay. So I will assign probably sections 8 point. We'll just do 1 and 2 next time because you guys have a quiz to study for too. We'll eventually get the rest of it. Okay. All right, in the time that we have left, we're going to talk about positional number systems in any random base. Okay, we are accustomed to positional number systems with base 10. We have base 10 fingers, so it just makes sense for us to use base 10. But there are other positional number systems with different bases, and like computers don't use base 10, they use other bases. Okay, so what a positional number system is every digit has a position and a number, and that position is important. It tells the sort of the weight or the value associated with that particular digit. Okay, and then the value or the weight that's associated with that position is some power of whatever the base is. So, for example, if we talk about, okay, the number 142, okay, the 2, we would call that, it's in like the ones position. Okay, so this one would be a 10 to the 0 position. The 4, we call that as in the tens position. Well, the weight of that position has a lot more weight than this position. This one has a weight of 10 to the first. And the 1 over here, that's in the hundreds place, or we could ask that has a weight of 10 squared. So if we were going to figure out how much this sequence of digits was worth, we would take 1 and multiply it by 10 squared, and then we'd add on 4 times 10 to the first, and then we'd add on 2 times 10 to the 0. So we do each digit and what it's worth times its position, whatever the weight of its position is. So that's what makes it a positional number system. And so if you think about Roman numerals, for example, or it's not a positional number system. Sometimes you subtract the numbers, sometimes you add them, depending on whether the small one comes first. Like that's not a positional number system, and that's why it's hard to like add them up and stuff because it's not positional. Okay. If you have even decimal numbers, it works the same way. Okay, so this is, 2 times 10 squared plus 0 times 10 to the first plus 7 times 10 to the 0 plus, and then if we go down in positions, notice what's happening with our exponents. That's 2, 1, 0. They're going down in number. So this 1, the weight of its position is 10 to the negative 1. And the 3, the weight of its position is 10 to the negative 2. Okay. So we can get any number that we want, fractions, integers, okay, using a positional number system by just putting the appropriate weight on each position. Okay, so we do that in base 10, but that's not unique. We could do that in any base. We could do that in base 5, in base 8, in base 17. Okay, I don't know if I would like to do it in base 17, but we could. Okay, and so we're always going to figure out how to represent the number by doing the same thing. We just say, okay, well, we assign weights. Whatever our base is, we have a b to the 0 position, a b to the 1 position, all the way, up as many as we need, and we can always find numbers to multiply each position by so that they'll add up to whatever our number is. And we can always find some base b representation of any kind of number. So let's think about how we would convert some number in base B, so any random base B, to the numbers that the way we think of, and decimal numbers. Okay, so a number in base B is just we're going to put whatever digits they use, and then in parentheses, and then the little subscript B after it to let us know that we're talking about a number in this base. Okay. So, for instance, if I have this number, 1203, and it's in base 3, okay, so if we think about that, well, this, okay, if we're a base 10 number, that would be in the 10 to the 0 position. But this isn't a base 10 number, this is a base 3 number. So this is in the 3 to the 0 position. Okay. So the base tells the weight of every position. This is the 3 to the first position. This is the 3 squared position. This is the 3 cubed position. So in base 3, we have a 1's place, a 3's place, a 9's place, and a 27's place. Not a 1's place, 10's place, 100's place, 1000's place, right? Same idea as base 10, it's just we're using a different base. We're using base 3 instead of base 10. And if you think about the way that we figured out the value of a number in base 10, it's just the same way. We're going to take the value of the digit in this position, which is 1, and then we multiply it by its weight. Well, it is worth, it's in the 27's place. It's worth, that should be times 3 cubed. And then there are 2 in the 3 squared place. And then there's nothing in the 3 to the first place, and then there are 2 in the 3 to the 0th place. So now if we just do all of that in base 10, I'll figure out the equivalent base 10 number. So this is 27, this is 18, that's nothing, that's 0, and then this is 2. Okay, so that's 47 in base 10. Now, computers don't use base 3. You're probably not going to run across base 3 numbers that often, but you will run across base 16 and base 8 and base 2 numbers quite a bit, so yeah, well, we have enough time. All right, so we have enough time to do this one. We'll do this one next time. So if we're talking about base 16, also called hexadecimal, so when you see the word hexadecimal, that means base 16. Okay, we have to have 16 different digits to use. So we can use 0 through 9 like we're used to, but then we run out of digits. Okay, so when we go to, so if we want to go up to the 10th digit, so A has a weight of 10, so we're going to do 0 through 9, and then 10 is A, 11 is B, 12 is C, 13 is D, 14 is E, and 15 is F, and that will give us the 16, 0 through 15, that's 16 different symbols that we can use, and then these of course have weight 0 through 9, and then A has a weight 10, B has a weight 11, and so on and so forth. So if we want to figure out what this one is in decimal, okay, so the A, that's worth 10 in decimal, so that would be 10 times, and then this is the 16 to the what place? To the third, so 16 to the 0, 16 to the 1, 2, 3, so this would be times 16 to the third, and then we would have 0 times 16 squared, and then 3 times 16 to the first, and then E has a weight of 14, so that's like 14 times 16 to the first. And somebody has to do this on their calculator for me. 16 to the third, I don't know. I'm sorry, guys. Does somebody here? I'll grab my calculator and then we'll be free. We'll see if you can get it faster than I can.
Wouldn't the E be 16 to the 0?
Thank you. I said 0, I think, but I did not write it correctly. Okay, so I got 41,022. Okay. On my calculator. All right. We're out of time. We'll work on some other conversions next time. Don't forget quiz on Thursday on sections 6.3 and 4, so on partial orders and equivalence relations.